So I'm standing here in front of you as a computer scientist, which is my way of saying, please accept a lot of butchery of the domain science and the free reign that I'm going to take with a lot of the domain science. What I hope to do over the next 15 to 20 minutes is pick up on where Romy left and where she discussed the importance of thinking about systems that are more complex at greater scales, but not talk about any one particular system, but again, at a level of abstraction, try to think about what is needed if we want to be able to design software systems that allow us to make the methodological and algorithmic advances that will support such investigations of complex systems at the scales that she mentioned. So I have two parts to my talk. The first part is to think about the implications of the software systems, the workflow systems that will support the kind of algorithmic and methodological advances that are needed for the science questions that Romy and others here have alluded to. And then the second part will be to take absolutely the simplest example of how some of those software systems are already having an impact in our ability to design interesting, novel workflows, which I'll call for the moment adaptive workflows. And this is work done in conjunction with several colleagues, most prominently Peter Casson, who's here, Michael Schertz, and others. So with that, let me step back and remind all of us why a fresh perspective to workflows and workflow systems is required. It's nice to see Scott in the room. Scott, and here's a shameless plug, Scott and I are co-editing a special issue on workflows for the Computing in Science and Engineering. And some of the same reasons that we're co-editing this special issue have cast a shadow here. Historically, workflow systems arose in big science projects like the Large Hadron Collider, projects like LIGO, where you had dozens of computer scientists supporting thousands of domain scientists. Statement number one. Statement number two, historically, the number of workflows, the number of different, if you will, pipelines was very limited. Within the whole of LIGO, there are approximately 30 or 40 workflows, but 95% of all computation is devoted to one or two, for example. So, and then obviously there are issues about the software ecosystem and the maturity that existed when these large projects began back in the late 80s, early 90s, versus the software ecosystem that is to be found today. Long story short, the implications of that is, once upon a time, it was the right approach to go with monolithic workflow systems, integrated workflow systems. But that is no longer valid today. Today, workflows are the epitome of the algorithmic and methodological advances that scientists make. There are many, many more workflows in the sense that if you think about the ability to, the many methods that are being developed, they're all fairly different. And arguably, the most important difference is that today the distinction between a workflow user and a workflow developer and a workflow system developer is less stark and less distinct as it was in the era of big science. This requires a fresh perspective to the thinking of how we design, develop workflows so that some of the scales that we've seen that are needed are still attainable without a lot of the overhead. What I wanted to say is that if you came in late or if you forgot what I was saying, the crux of the introduction was that in order to support the methodological and algorithmic advances that are needed to achieve the kind of science questions that Romy and others have alluded to, you need a fresh perspective on workflows. And the historical approach to workflows will not work in order to support the methodological advances. And a single one-size-fits-all is inadequate. Okay, so as I said, I'm going to take a slightly formal computer science approach, but very quickly, in order to be able to explain to you our contributions and how a lot of this has happened on BlueWaters, allow me to just give you some background. Think of the world of distributed cyber infrastructure as organized around 4 layers. At the bottom layer is the resources, and clearly BlueWaters falls here. Think of a level 2 description as that of the task runtime, and remember here task, and for the rest of my talk, is a standalone simulation, a computational processing element. Then there's the workload as opposed to workflow management, and the workload is the aggregation of tasks that you have that need to be executed, right? So, and the workflow, the distinction between the workflow and the workload here is essentially the fact that the workflow has the full dependencies which haven't been resolved, whereas the workload are the set of related tasks and the execution descriptions, but the dependencies have been resolved. So when you're given a workload, you can start running all the tasks that comprise the workload, okay? So again, very general, but that's the mental model to keep in mind for the rest of the talk, and we'll really be talking about workloads. Okay, and the specific contribution to going from the abstract to a specific software realization of all of these is the Radical Cyber Tools suite, and there are Radical Cyber Tools at each of these components. The hero of the show today is what I'll call the Ensemble Toolkit, which reflects the title of the talk, Power of Many, beg your pardon. Okay, and we'll come back and discuss both the Ensemble Toolkit and the lower lying runtime system, which we call Radical Pilot. The important point here is, again, a talk unto itself, is that this is the building blocks approach to building workflows and workflow systems. And the one message, again, I want to convey from a software and abstractions point of view is that there isn't a predetermined ordering or set of components that you can use. The whole idea is that each of these components, building blocks, can be used standalone without, let's say, the other lower layers, or, and more equally importantly, they can be extended and used by other domain-specific workflow systems. So they both provide well-defined functionality as well as being extensible and integrated with other existing tools. And what I'm going to do in the next few minutes, and whereas I'm going to focus on biomolecular sciences, I just want to leave you with a quick overview of the kinds of science problems that are being used, cyber tools are being used for. There's a whole set of streaming applications if you think of the various light sources that come off these facilities, synchrotrons and free electron lasers, and there's a need to try to integrate streaming data with high performance computing resources. There are a whole set of seismic physics applications where you're trying to do both the adjoint simulations as well as several of the inverse problems. And then there are a whole set of purely data analysis tasks where you need to analyze volumes and large volumes of data in as short a period of time as possible in order to keep the simulations ready to run. And we've got all of, with the exception of this, we've got all of these working on BlueWaters, but I won't talk about these today. There are references, we can be glad to share them with you. What I want to talk about today is the algorithmic innovations that are required for the scientific advances we heard this morning, and then obviously how the cyber tools approach to building workflows and workflow systems supports that. So at the root of all the advanced workflows is the need to do efficient resource management with many multiple tasks. Now, these tasks, as I alluded to, could each be an individual simulation, one node simulation, or multi-node MPI. And the pilot abstraction, which has been studied over a large number of years but has been formalized more recently in this paper and elsewhere, gives you this multi-level approach to performing resource management. And on BlueWaters, in the case of being able to run many, many tasks, here just to give you a sense of how challenging this can be, you're trying to order thousands of MPI tasks, how do you know you're utilizing your resources carefully? This is several PhD topics in of itself. And this starts giving you a sample. This is not exactly BlueWaters, this is on Titan. But I chose Titan because we have a better sense of how this becomes challenging when you're running 4,096 MPI tasks concurrently on approximately 128K cores. And you can see managing and keeping the resources busy with this many number of tasks is a highly non-trivial exercise. And there are a large number of underlying research challenges that have been required that we've overcome in order to get to what I would say is about 50% utilization on very short running tasks. Okay, as I said, the hero of the show is the Ensemble Toolkit. Think of this as a layer on top of Radical Pilot, which allows you to manage the complexity of resource acquisition as well as application execution for ensemble-based applications. Now, whether these are replica exchange or large adaptive ensemble workflows, the whole idea is you've provided the right set of abstractions user-facing and the right set of abstractions downward-facing so as to make this easier. And the whole idea is to make it easier for the domain scientists so that now the algorithmic innovations that they have can be tested at scale, right? And lots of details in how this happens. Just maybe the really the high-level idea is that there's a well-defined programming model comprised of what is called the PST model, pipeline, state, and task. And nearly all applications that are of relevance in the biomolecular space for ensemble approach, that use ensemble approaches, can be captured using this approach. There's a whole set of, if you will, internal system details of how to ensure that the simplicity of this programming model is still supported at scale with the adequate performance. Okay, and this is again just a quick schematic to convey 2 points before I get to the final few slides, is that this is a set of seismic physics ensemble simulations where each simulation is running over 384 nodes, and you get good, strong, and weak scaling over a fairly large fraction of the machine, but you also start seeing large numbers of failures suddenly at a very high node count. And this has nothing to do with the programming system itself, but this goes back down into understanding the complexity of running a very large number of concurrent MPI tasks with the MPI distribution that comes on these Cray machines. And we're still trying to figure out, working with Cray, why exactly there is a spike from essentially 0 failures to a very large fraction of failures. Okay. The one example I want to talk about in terms of building a tool on top of the Ensemble Toolkit that supports a large number of workflows is the high throughput binding affinity calculator. And binding affinity calculations are important, pervasive in the drug industry, but also for many other biomolecular simulations. So if nothing else, I want you to appreciate the building blocks approach. There is the runtime system I alluded to. There is the Ensemble Toolkit, which has the PST model. And on top of that, there is a domain-specific workflow developed by people at University College London, which has its own abstractions. But importantly, they do not have to worry about any of the low-lying details. They are able to use the PST model, and as I will show you in a few seconds, able to develop fairly sophisticated workflows, trying and working at extremely large scales. Remember my first slide, the objective was to allow the workflow developer and the workflow user to become essentially the same. And this is a step in that direction because now they are able to use the building blocks below to do this. There's one interesting, in the interest of time, maybe I should just try to show you some scaling plots. This is for a particular protocol to compute the binding free energy, which goes on, in this case, BlueWaters, to 16,000 cores. And once again, you can see the strong and the weak scaling. So what is this protocol? as I said, I'm going to take liberties with the science. It's really a thermodynamic integration. And there's a whole, if you will, set of details that I won't be able to cover. But the important point here is that the placement of the lambda windows is a decision. The exact values and the placement of the lambda windows is something which can be determined at runtime based upon the data and the analysis that has happened so far. Thank you. And that's the one mode of adaptivity that this protocol requires support from the underlying runtime systems. So as I said, I'm not going to focus on what good science comes out of it. I want to show you how, by designing workflow systems that support this kind of adaptivity, what computational advances arise. And what this tells you is to compare the workflow I showed you on the previous slide, take the non-adaptive implementation and take the adaptive implementation, and for just one drug candidate, look at the number of core hours that are consumed. And you can see that the adaptive implementation gets you lower errors for the same amount of resources utilized, gives you lower errors. So that's statement number one. Statement number two, that this is true for a large number of drug candidates. So these are 5 different drug candidates, and invariably, you'll find that the time series shown on the slide before is not one-off, but it is out of 5 cases. In 4 cases, the adaptive formulation of that workflow gave you, for the same amount of resources consumed, gave you the much better errors for the same for resources consumed. Okay, and this is trying to show you, when you fix the amount of resources consumed, that the error, this is the error difference over the 5 different approaches. And what all of this put together tells you that you can start making real-time trade-offs between accuracy and computational cost while really using 1/2, 1/3 of BlueWaters. And this is just one example from last month's scale, where we showed that by the combination of adaptive runtime decision making and the scale we can run at, we were able to process a very large number of drug candidates and a step towards clinical insight. And again, all of this work was done on BlueWaters. And the whole idea as a computer scientist is not to do this one-off. The advantages that we've demonstrated in the case of binding free energies must be generalizable, must be valid for other forms of adaptive algorithms. Working with Peter and Michael, Michael Schertz, we've been thinking about what's the normative execution model for adaptive workflows, and what are the different types of adaptivity, and making sure that these are supported in a first-class context. We show that even though adaptivity may not always lead to the kinds of improvement we talked about, this graph tells you that a domain scientist like Michael Schertz and his graduate student can start playing around with different forms of methods, different algorithms, to quickly prototype at the scales necessary to determine which are the good methods, good algorithms, versus which are the bad ones, or not so good ones. And this is just trying to show you that this is really testing algorithmic advances at very large scales for those kinds of algorithms that are not trivial to both develop as well as deploy. In summary, in order to reach the kinds of sophisticated and complex science problems that we've heard this morning and earlier, we need advances in our ability to try to support algorithmic and new methods. But this in turn imposes very interesting and very challenging constraints on how we develop, deploy, and execute workflow systems. And what I've hopefully shown you is that the building blocks approach, an instance of which is the radical cyber tools approach, allows you to think of these sophisticated workflows and workflow systems without any of the overheads of your traditional monolithic workflow systems. Thank you.